A Formula One car is just one of the most incredible machines we've ever built. But it's so much more than just an engine and four wheels. It's really a masterpiece of material science. So in this explainer, we're going to break down what an F1 car is actually made of. And I promise you, the answer is way more surprising than you think. Let's just start with a simple number. Okay, get this number in your head, 798 kilograms. That's it. That's the minimum weight of a modern F1 car, and that includes the driver. I mean, for a machine that's pushing over 1,000 horsepower and pulls G-forces that would make a fighter pilot black out, that is just ridiculously light. And right away, that lightness brings us to the central mystery, right? If the car weighs less than your average Kia, how on earth does it cost millions and millions of dollars to build? The weight and the cost, they just don't seem to connect at all. So what is going on here? Well, to start figuring that out, let's just look at what the car is physically made of. I mean, if we were going to break it down by sheer weight, by what's heaviest, there is one material that is absolutely king. And that king is carbon fiber reinforced polymer, or CFRP. Now, this isn't just one thing, it's a composite. Think of it like this. You take these unbelievably strong but super light carbon fibers and you bake them into this tough epoxy resin. What you get is a material that's just mind-blowingly strong, incredibly stiff, and weighs almost nothing. It's the perfect thing to build the chassis, the body, the wings. I mean, it's pretty much the car's entire skeleton and skin. And when you look at it this way, it's kind of crazy just how much of the car is carbon fiber. By mass, a whopping 65% of the car is CFRP. I mean, all the metals combined don't even make up half of that, sitting at just 28%. So looking at this, you'd probably think, okay, an F1 car is basically just a really fancy carbon fiber sculpture. But that other 28%, that is where things get really, really interesting. Because we're not talking about just any old chunk of metal here. We're talking about a carefully chosen symphony of alloys where every single one has a very specific and very critical job to do. So you've got titanium, which they use for parts that absolutely positively cannot fail, like the suspension bits. Then you've got your aluminum, which is perfect for stuff like radiator housings where you need it to be light, but you don't need that brute strength of titanium. Steel is for parts that take a beating over and over. And then there's magnesium, even lighter than aluminum, but they use it carefully because, well, it's flammable. And this right here just perfectly shows you the constant balancing act that F1 engineers are playing. Just look at titanium versus aluminum. Titanium is way, way stronger, but the cost to make a part out of it is astronomical, partly because it's so tough to machine. Aluminum's cheaper, easier to shape, but you just can't use it for everything. Every single bolt and bracket on that car is the result of a decision just like this one. Okay, so we know the car is mostly carbon fiber by weight, but this is where we take a huge pivot, because looking at the car by mass, it's like only reading the first chapter of a book. It doesn't tell you the real story at all. And that brings us right back to our big question. If 65% of the car's weight is carbon fiber, does that mean 65% of the cost is carbon fiber? And if not, then where in the world is all that money going? So let's just look at this chart one more time. Burn this picture into your brain. Carbon fiber is the huge, dominant slice of the pie. You got it? Okay, because things are about to get turned completely upside down. And here it is. This is the reveal. The moment we reslice that pie based on value, the picture changes completely. Carbon fiber's share gets slashed down to 40%. And look what happens. Suddenly, titanium is worth 18% of the car. The incredibly complex electronics in the hybrid battery, that's another 18%. And the brakes? Get this. The brakes alone, made of a special carbon-carbon material, make up a full 10% of the entire car's cost. So here's the big secret, right? It's not about how much the raw material costs. The true value of an F1 car comes from something totally different. Insanely complex manufacturing, super specialized processing that can take hundreds of hours, and, of course, the use of rare and exotic materials. I mean, just look at these examples. Titanium is expensive to buy, sure, but it's a total nightmare to machine into intricate shapes, and that labor is what sends the cost sky high. Those brakes can run at a blistering 1,000 degrees Celsius, but the process to actually make them is incredibly time-consuming and expensive. And the electronics and the battery, well, they're just packed with high-value stuff like rare earth elements, lithium, cobalt, and copper. Once you see it this way, you have to start thinking about an F1 car in a completely new light. It's not just a racing machine. In a lot of ways, it's basically a treasure chest of high-value commodities on wheels. And you find this stuff in the most amazing places. Teams like McLaren famously used a thin layer of actual gold foil as a heat shield in the engine bay. Yeah, literal gold. You've got platinum group metals and critical sensors, the powerful electric motors in the hybrid system. They absolutely depend on rare earth elements like neodymium and dysprosium. Even silver gets used in some specialized electronics. So the big takeaway is this. An F1 car's real identity isn't defined by its most common material, it's defined by its most valuable ones. It's a precisely engineered collection of global commodities, where just a few grams of a rare metal can be way more important and way more expensive than kilograms of carbon fiber. And that just leaves us with one final thought to chew on. We've seen how today's cars are defined by this incredible balancing act between weight, strength, and cost. So as technology keeps racing forward, you have to wonder, what incredible, maybe even priceless, new material is out there that's going to build the Formula One car of tomorrow?